Right now, a single American stealth fighter like the F-35 costs over $80 million. The total program to develop and build them will end up costing American taxpayers more than $1.7 trillion over its operational lifespan. For decades, that massive investment bought the United States complete military dominance in the sky. Stealth aircraft are engineered with razor-sharp geometric angles and coated in special radar-absorbing materials. When a standard military radar shoots a powerful wave of radio energy into the sky, a stealth jet doesn't bounce that energy back to the dish. It absorbs the energy or deflects it away at an angle. To a conventional radar screen, a multi-ton supersonic warplane looks no bigger than a songbird or a floating leaf. Then Chinese defense researchers at the China Electronics Technology Group Corporation built a radar that doesn't care about radar-absorbing paint or geometric angles. It is called a quantum radar. It doesn't send out giant pulses of radio waves and wait for an echo. Instead, it uses a branch of subatomic physics that Albert Einstein famously called spooky action at a distance. It splits pairs of light particles, sends one particle out into the sky, and keeps its twin locked inside a laboratory receiver. When the outgoing particle hits a solid object, even an advanced stealth fighter flying through a blinding tropical monsoon, the system registers a microscopic quantum shift. The storm clouds don't blind it. Heavy rain doesn't hide the aircraft. Advanced electronic jamming systems can't scramble the signal. If this technology works reliably outside the lab, it turns the core strategic pillar of Western air power inside out overnight. It means the vast majority of America's modern tactical aircraft could be exposed to ground-based air defenses in a high-intensity Pacific conflict. And to understand why military analysts from Washington to Beijing are quietly obsessed with this breakthrough, you first have to look at the trillion-dollar physical trick that quantum radar was built to expose. To understand why a quantum radar is so disruptive, you have to look at how traditional stealth actually works. There is a common myth that stealth aircraft like the F-22 Raptor, the F-35 Lightning II, or the B-2 Spirit are completely invisible to radar. They are not. Stealth is not a magical cloaking device from a science fiction movie. Stealth is simply a carefully engineered game of physical deflection. A standard military radar works like a person standing in a pitch-black room holding a powerful flashlight. The radar dish shoots out a concentrated beam of high-frequency radio waves into the sky. If those waves hit a normal metallic airplane, like a commercial airliner or an older fighter jet, the flat metal surfaces, curved wings, and engine intakes reflect those radio waves straight back to the receiver dish, like a mirror bouncing flashlight beam back to your eyes. The radar system measures how long the wave took to return, calculates the angle, and places a bright dot on a tracking screen. Stealth engineering changes that geometry entirely. Aircraft designers use two main tricks to break the radar loop. First, they design the airplane's fuselage using precise mathematical angles. Instead of bouncing the radar waves straight back to the ground dish, those sharp angles reflect the incoming radio energy away sideways or upward into space. Second, they coat the skin of the aircraft in complex radar-absorbent materials. These specialized chemical coatings take incoming electromagnetic energy and trap it, converting the radio wave energy into harmless heat instead of letting it bounce back. This combination reduces an aircraft's radar cross-section down to almost nothing. To an enemy air defense radar, a massive strategic bomber looks like a tiny plastic marble floating 5 miles high. For 40 years, this trick gave the United States air superiority over every adversary on Earth. American military strategy assumed that in any major conflict, stealth bombers and fighters could slip silently past enemy air defense nets, destroy command posts, and neutralize missile sites before the defending nation even knew an attack was underway. Trillions of dollars were poured into building military forces around this exact capability. But every stealth trick relied on one single physical assumption, that the radar on the ground would always send out standard electromagnetic waves, and wait for those same waves to bounce back. The moment someone engineered a radar that stopped relying on standard wave reflection, the entire foundation of modern air power began to crack. The physics behind quantum radar sounds complex, but the core concept can be understood using a simple real-world comparison. Imagine you are standing at a noisy, crowded concert hall where thousands of people are shouting at the top of their lungs. If someone on the far side of the room yells your name, you will never hear it. The background noise easily drowns out their voice. But what if you and a close friend had a pair of magic wristbands that vibrated in exact sync, no matter how far apart you stood? If your friend taps their wristband on the other side of the room, yours vibrates instantly on your wrist. You don't need to hear their voice through the crowd. You know instantly that they tapped you because your wristband reacted right in your hand. That is the exact principle behind quantum illumination. Inside a quantum radar system, engineers use specialized crystals and precise lasers to create what physicists call entangled photon pairs. Quantum entanglement is a physical phenomenon where two subatomic particles become deeply linked at a fundamental level. Whatever happens to one particle instantly affects or correlates with its twin, regardless of the distance between them. The radar machine takes this stream of twin photons and splits them up into two separate jobs. One photon, called the signal photon, is converted into a microwave pulse and fired out through an antenna into the sky, searching for targets. Its twin particle, known as the idler photon, never leaves the radar system. It is kept trapped inside an ultra-cold, highly isolated laboratory receiver right on the ground. The signal photon travels through the atmosphere. If it hits an object in the sky, whether it's a massive commercial transport plane, a heavy storm cloud, or a high-tech stealth jet designed to absorb radio energy, that photon bounces off and travels back toward the ground dish. When that returning signal photon hits the receiver, the radar doesn't just measure how strong the wave is, because the returning signal might be microscopic. Instead, the computer compares the incoming particle directly against the idler twin it kept safely inside the lab. Because the two particles share a fundamental quantum correlation, the receiver can instantly tell if the returning particle is its original twin or just random background noise. Even if 99% of the energy was absorbed by stealth paint, deflected by angled wings, or scattered by atmospheric interference, the quantum link between those two twin particles remains intact. The stealth jet's geometric tricks don't work anymore because the radar isn't waiting for a big reflection. It is simply matching quantum fingerprints in real time. Understanding how quantum radar handles physical stealth geometry is only half the equation. To truly grasp why military strategists are watching this technology so closely, you have to look at how traditional radar fails in real-world environmental conditions, and why quantum mechanics completely changes that dynamic. Conventional military radar systems have two massive enemies: natural weather and artificial electronic warfare. When a storm front rolls in over an ocean or a coastal defense zone, the sky fills with billions of dense water droplets, heavy rain, thick fog, and turbulent ice crystals. When a standard high-frequency microwave radar fires its energy beam into a tropical typhoon, those water droplets act like millions of tiny mirrors. The radar waves scatter wildly in every direction. The energy bounces off rain clouds, reflects off ocean waves, and creates massive visual clutter on the operator's screen. High-performance radar operators call this atmospheric noise. In severe tropical weather, a stealth jet doesn't even need its high-tech skin to stay hidden. The storm itself creates an impenetrable blanket of clutter that blinds standard radar dishes. On top of natural weather, modern military jets carry advanced electronic warfare pods. When an enemy radar locks onto a fighter jet, the jet's electronic countermeasures fire back high-powered jammer signals. These jammers flood the airwaves with fake radar returns, ghost targets, and intense electronic noise, confusing the ground station and hiding the aircraft's true location. Quantum radar turns both of these defensive strategies completely upside down. Because a quantum radar relies on matching returning signal photons with the idler photons kept inside its receiver, it possesses an extraordinary filter against environmental noise. Heavy rain droplets, dense sea fog, and tropical storm clouds scatter radio waves, but those rain droplets cannot produce quantum-entangled particles that match the exact quantum fingerprint of the idler photons sitting in the ground station. When a deluge of scattered noise hits the quantum radar's dish, the system's processor instantly discards every single particle that doesn't match its internal twin. The rain clouds become completely transparent to the processor. The ocean clutter vanishes from the calculation. The storm disappears. The exact same rule applies to high-tech military jamming systems. An enemy electronic warfare pod can flood the sky with millions of powerful fake radio signals, but it cannot clone the exact, unpredictable quantum states of the entangled photons stored inside the defender's ground station. The jammer's fake signals are simply recognized as untagged background noise and erased from the screen in milliseconds. The very environmental conditions that normally hide a stealth fighter, blinding monsoons, thick cloud cover, and heavy electronic interference, actually make quantum radar's comparative advantage even stronger. The darker and noisier the sky gets, the clearer the quantum fingerprint stands out against the background. Despite the world-altering headlines and theoretical breakthroughs coming out of Chinese research labs, a crucial question remains: can quantum radar actually leave the laboratory and survive on a real-world battlefield? Skeptics in Western defense circles point out that subatomic physics in a highly controlled laboratory is vastly different from an operational military radar operating on a humid, salt-stained coastline in the South China Sea. Building an operational quantum radar requires overcoming three massive engineering hurdles that have stumped physicists for decades. The first major hurdle is what scientists call quantum decoherence. Entangled photons are remarkably fragile. The moment a signal photon leaves the radar antenna and travels through warmer air, atmospheric turbulence, or high humidity environments, its delicate quantum state can be easily disrupted. If the photon loses its quantum link before returning to the dish, the radar loses its primary advantage over standard sensors. The second obstacle is target distance. To detect an incoming supersonic aircraft early enough to launch air defense missiles, an operational radar needs an effective range of at least 100 to 200 miles. In early laboratory tests, generating and detecting single entangled photons was limited to very short distances. Squeezing enough power into single photon emitters to push quantum beams through dozens of miles of heavy atmosphere requires ultra-advanced optical technology and massive computational processing power. The third challenge is system cooling and physical hardware. The single photon detectors used to measure returning signal particles traditionally require cryogenic refrigeration, cooling equipment down to near absolute zero temperatures. Mounting cryogenic lab gear onto mobile military trucks, naval destroyers, or rugged radar stations is an engineering nightmare that takes years to refine. However, dismissing China's quantum progress as pure science fiction would be a severe strategic mistake. The China Electronics Technology Group Corporation, along with top research teams at the University of Science and Technology of China, have made rapid strides in solving these exact hardware constraints. Rather than attempting to build a giant, standalone quantum super radar overnight, Chinese military engineers are developing hybrid systems. These platforms combine standard high-power radar beams with quantum illumination sensors operating in parallel. Furthermore, recent breakthroughs in room temperature single photon detectors and high-frequency microwave quantum converters are rapidly shrinking the size and power demands of these machines. What used to fill an entire climate-controlled university laboratory is slowly being compressed into modular, field-deployable units. The transition from quantum theory to field deployment is not happening overnight, but it is moving steadily forward. The technological race is no longer about whether the physics works, but about which global power can harden the fragile hardware fast enough to integrate it into an active air defense grid. If quantum radar technology completes its transition from high-tech military laboratories into active, networked air defense batteries, it signals the end of an era that has dominated strategic military thinking for nearly half a century. Since the late Cold War, Western military superiority has relied heavily on one fundamental assumption, that spending billions of dollars to make an aircraft invisible to radar provides an unmatchable strategic advantage. This doctrine dictated how the United States spent trillions of taxpayer dollars shaping entire generations of military hardware, from the F-117 Nighthawk and the B-2 Spirit to modern mainstays like the F-22 Raptor, the F-35 Lightning II, and the newly unveiled B-21 Raider strategic bomber. If ground-based quantum sensor networks render radar-absorbent coatings and sharp geometric angles ineffective, the economic and tactical math of modern warfare shifts dramatically. An F-35 fighter jet costs roughly $80 million to manufacture, with astronomical maintenance expenses required just to keep its delicate radar-absorbing skin intact after every flight. If a ground-based quantum radar array can track that aircraft through heavy cloud cover and electronic jamming regardless of its stealth shape, that multi-million-dollar invisible armor becomes a costly liability. This structural shift forces military planners in Washington, London, and Tokyo to fundamentally reconsider future combat doctrines. If stealth no longer guarantees invulnerability in contested airspace, air forces cannot rely on small fleets of hyper-expensive, radar-evading warplanes to breach enemy defenses. Instead, military engineering will have to pivot toward entirely different tactical parameters: extreme hypersonic speed, overwhelming mass, long-range standoff weaponry, and autonomous robotic swarms. Rather than trying to hide from modern sensors, future doctrine will focus on outrunning missiles, overwhelming air defense computers with hundreds of low-cost attritable drones, and deploying advanced electronic warfare that attacks the communication networks binding enemy sensor grids together. The United States Air Force's Next Generation Air Dominance Program, commonly known as NGAD, is already adjusting its future designs to reflect this reality, placing less emphasis on pure geometric stealth and far more focus on unmanned teammate drones, artificial intelligence, and directed energy countermeasures. The emergence of quantum sensing marks a classic historic cycle in military history. Every time an offensive technology achieves complete dominance, a new defensive breakthrough emerges to neutralize it. Armor leads to armor-piercing rounds, high-altitude bombers lead to surface-to-air missiles, and now, radio frequency stealth faces its ultimate physical counter in the quantum realm. For the past 40 years, the world's most powerful militaries operated under a single, unchallenged rule. Whoever controls the electromagnetic spectrum controls the sky. The nation that could build the sleekest jet, coat it in the most advanced radar-absorbing material, and reflect radio waves away from ground stations held the absolute power to strike anywhere on Earth without warning. That single technological advantage cost trillions of dollars to develop, but it guaranteed complete military dominance for an entire generation. China's push into quantum radar proves that even the most dominant military strategies eventually run into the unyielding limits of physics. By shifting the battlefield from macro-level radio waves down to subatomic particle correlations, quantum illumination exposes the fundamental vulnerability of geometric stealth. It reminds military planners that physical shapes and chemical paint are only effective against the specific wave frequencies they were designed to deceive. The moment a sensor stops measuring simple wave reflections and starts tracking entangled subatomic states, the multi-trillion-dollar invisible shield begins to dissolve. This shift does not mean stealth aircraft will vanish overnight. The sheer difficulty of mass-producing rugged, battlefield-ready quantum sensors means traditional stealth fighters will continue to fly, patrol, and project power for years to come. but the golden age of undisputed aerial invisibility, where a small group of high-tech warplanes could enter contested airspace entirely undetected, is officially coming to a close. The global military arms race is no longer just about who can build the fastest jet, the stealthiest bomber, or the most powerful missile. It is rapidly becoming a race over who controls the quantum sensor grid. The country that masters microscopic particle entanglement will be able to see through blinding monsoons, pierce heavy electronic jamming, and track every piece of metal moving through the upper atmosphere in real time. For decades, the strategic advantage belonged to the attacker hiding in the dark. In the century ahead, that advantage is shifting directly back to the defender holding the quantum light. If quantum radar makes traditional stealth jets visible to ground air defenses, should the US military keep spending billions on new stealth bombers or pivot entirely to hypersonic missiles and autonomous drone swarms? Drop your thoughts in the comments below. Hit that like button, subscribe, and turn on notifications so you don't miss what's coming next.